So we've talked about normal stress. So let's talk about the other type of stress that we have, which is shear stress. So again, shear stress is represented by tau. And this is the Greek letter tau. And it is given by the shear force, which we usually refer to as V over the area. Right? So shear, again, if you have some, maybe this is some beam, and you have a force acting here and a force acting here, then what you have is this beam trying to come apart. If you think about maybe a book or something like that, you take a book. If I take a book and I apply a force one direction opposite from the other, I can see that I kind of cause this area in the middle to experience this stress, right? I have this like sliding motion of my book against itself because I have one force going one way, one force going another way. We see this shear appear in the middle when we do this like cross-sectional cut, right? We get a shear force. So this cross-sectional area is the area of this beam. That's the area that we're looking at. It's the area that's being affected by the shear, right? So it's happening, the shear is happening in the same plane as the area. Whereas with normal stress, it was perpendicular. This is happening in the same plane. Shear and area are now in the same plane here. And typically where we find this shear stress is usually like at fasteners and interfaces where things connect together. So think like pinned connections, bolts, nails, glued joints, things like that. That's where we typically find this shear stress. For example, let's look at just a single shear case. So this is called single shear, when we just have one thing shearing against another. So for example, I have a plank of wood here that is pinned. There's a pin here going through this plank of wood I've nailed down. Let's say I've nailed down this plank of wood to this bottom plank of wood. Right, it looks something like that. And this pin here goes all the way down between the two. Right, so I have these two boards pinned together, and then they have this force that causes the boards to be pulled apart. So here some force is pulling this board, and I'm getting an equal and opposite reaction in this other board over here. So what happens on my pin is that it acts like a beam like this, right? Where I have the cross-sectional area is the area where these boards are meeting, where this thing is getting stressed, right? There, it's shearing against each other. It's kind of plate tectonic rubbing against each other there, but acting on this bolt. So in my single shear, my tau is going to be this F force that it's experiencing, just a single F force over the cross-sectional area of the bolt. So whatever this area here is. The area of this bolt or nail, whatever it is going to be this area here. Now, if it wasn't bolted, let's say maybe I had these two planks of wood, but instead they were glued together. So instead of a bolt, I have this, and it was glued right here to a board I stuck on top of it. Now my cross-sectional area is going to be this shaded area, this big square area here. So it depends on what type of fastener you're using, but it's always that area where those two surfaces are kind of rubbing against each other. That's how I think about it, as like where they connect. That one connection point is where that area is. So we can have more than just single shear. If we have two bolts, for example, or maybe another plank of wood, then we get what's called double shear. And this is where our force of our, let's do the 2 boards. Let's say here's a board. I've got a board underneath it. And then I have another board underneath that. All right, so I have these 3 boards stacked on top of each other. And I have my bolt that goes through all 3 boards. There's my little pin. This is a device called a clevis, if you're curious. This is you'll often see, you know, on like maybe like a bike. Here you have the handlebars, and this kind of comes around and attaches to your bike tire here. Here's like a bike tire, and then it's pinned through. I mean, well, bad example, because you wouldn't pin it on the tire here. You'd pin it through the middle, but you know what I mean. The front of your bike, where you'd have your handlebars up here, you would pin this through. This is the kind of device we're looking at. Super common. You see this all the time. These little double shear kind of devices. So in this, I have a 3 boards. Sorry. So board 1, board 2, board 3. And my board 1 is the one who's experiencing this force. Right? So some force is pulling on my board 1, but let's say my other side is fixed, so each of these 2 boards are having an equal and opposite response. Right? And they're each going to be getting half of the force F. Right? If we think about equilibrium, I have a force coming through this board and a force coming through this board to be equal and opposite. So they would each take on half of the force here. F over 2 and F over 2. So if we were to look at this bolt, kind of break it out, just the body of this bolt here, the force that this is experiencing, and this is the big board, right? So this board here, this center board, is causing force F, which is in turn causing shear at these plane interfaces right here between the boards and right here between the boards. Right? Between each of those boards, we're shearing. The bolt is being sheared. So this is the shear V that it's experiencing. And again, we see from equilibrium, we assume that we can see that these are equidistant apart, so they're each taking on half of the force there. We're assuming that V is taking on half of the force, so V is F over 2. And now if we plug that into our equation, now we see for double shear, our equation is, instead of tau equals F over A, tau equals F over 2 over A. Right? Because it's our shear. It's shear over A, and we say shear equals F over 2. So it's F over 2A. F over 2A. Where again, the area is this cross-sectional area of the bolt, each interacting at those interfaces. And this can go even beyond this, even beyond single and double shear. These are the most common cases we'll see, single shear and double shear, but there could be more, right? There can be more shear than that. And the way we account for that is, let's say I have this board here, and it's attached to this board here. But this one has 3 pins, let's say. Say boop, boop, boop. It's got 3 bolts connecting it down. Now, each of those bolts are creating another area, right? They're creating another interface area. So now, if I were to look at that board, right? So here's that bottom board. I have bolt 1, bolt 2, bolt 3, and the force that the board is experiencing, F. And then each of these experiencing a shear, right? So I have these 3 areas experiencing this shear. So for this example, my shear stress would be F over 3A, right? Because our F would equal 3 V's from equilibrium. Or you can think about them as 3 separate areas, giving us this new shear stress equation. So depending on what's actually happening, you're going to have to adapt this shear stress equation. Let's take a look at a couple of examples. So for this example, we are asked to determine the average shear stress in the 20 millimeter diameter pin at A and the 30 millimeter diameter pin at B. So when we look at this problem, where do we even start, right? We can kind of use our statics brain to be like, okay, well, I know I need some forces in A and B, so I'm going to need to go through and set up my equilibrium equations and solve for these reactions, right? So I'm going to draw myself a free body diagram over here because, yes, we love free body diagrams. We always love free body diagrams all the time. With 30 kilonewtons, I have my force through this cable here attached at BC, and then I have this pin at A giving a Y force and an X force. So easy enough, we've done this lots of times by now, setting up these equilibrium equations and solving for these reactions, right? So I can take a moment about A equals 0 and say, all right, 30 times 2, that'll be negative 30 times 2 plus the Y component of FB. Oh, I forgot they gave us a triangle here. A 3, 4, 5 triangle relationship. So going through and just, I'll spare you the rest of these details of this equilibrium equation here, but it's 4/5 FB times its distance away is 6, right? So we can solve and we can get FB equals, when I punched that into my calculator, I got 12.5 kilonewtons. And then of course I would do the same with my sum of X equals 0 and sum of Y equals 0. I'm going to go ahead and skip that step for now and just go ahead and give those reactions as our AX 7.5 kilonewtons and AY is 20 kilonewtons, right? I expect that should be pretty straightforward. You can solve that on your own. We want to get to this shear stress portion, right? So let's go ahead and let's actually start with the 30 millimeter diameter pin at B. Right, so if we look at kind of what the side view of this looks like, what I have happening at B is we have this bottom connection pin here, right, with this rope that goes off. There's the cable that goes off in the distance, and then it's connected to, or pinned to, I should say, my beam down here, so that connects to the beam, and these are pinned together. Here's my little pin rod coming down through here. They're pinned together. Right, so I know what my FB is. I know what the force in this cable is. We just calculated FB as 12.5 kilonewtons. Right, that's our FB. And then since we assume equal and opposite, this is in single shear. There's only there's only this rope portion and then the other side of the beam portion. So this would be, this is in single shear at pin B. So single shear at pin B, I know that my other side is also experiencing this 12.5 kilonewtons. So we can calculate that shear stress. Right? Our shear stress tau at B is going to be the shear over A. We know this shear in this case is just going to be equal to that force, 12.5 kilonewtons, over the area. And again, that area is the cross-sectional area of the pin. So that would be our area of a circle is pi over 4d squared. They gave us our diameter was 30 millimeters. I'm going to go ahead and convert that over. Pi over 4 times 0.03 meters squared. I need to do a unit conversion. I didn't convert that top unit, my kilonewtons. That's okay, I can convert it as I punch it in my calculator here. And I get the shear force experienced by the pin at B is 17.7 megapascals. 17.7 megapascals. Right? Pretty straightforward. The hardest part about these guys will be determining whether you're in single shear, double shear, more than that, or sometimes the cross-sectional area can be a little bit tricky to see. So let's look at this pin connection over here. Right? This pinned connection at A. Now they also gave us a cross-sectional view for this, but now instead of being in single shear, we're actually going to be in double shear at pin A. So the diagram they gave us here was that our beam was attached. So here's our beam attachment. That's a terrible drawing. All right. Well, anyways, here's kind of our beam attachment. The beam goes off that way. That's experiencing the forces of A, right? So it's that AX and that AY force are what is being experienced on the beam here. So FA, where FA is going to be the square root of AX squared plus AY squared. So both forces, the AX force and the AY force, are contributing to it. FA, I'll go ahead and calculate out now since we talked about it, that FA, when I plug in those values, 21.36 kilonewtons. It's FA on that beam there. But the pin is a clevis. It's a clevis pin. So it comes out like this, where it has one edge here and then one edge on the bottom as well. And they connect into a base that's somewhere, over here. So, oops. We have this pin going through it. Goes through the top, through the middle, and down through the bottom. So that the shear experienced is being experienced in two places, both at the top and the bottom of the pin here. Right, I have a V and a V. So since this is a double shear case, let's do this in orange. My shear stress at A is actually going to be, is still the V over A, but V in this case, 2V equals FA. So my V equals 2 over F, or FA over 2, right? FA over 2 divided by the cross-sectional area of the bolt. I'm going to have that 21.36 divided by 2 all over pi over 4 times d squared. And d, I believe it gave us in the problem, a 20 millimeter diameter pin. Oops, so converting to meters, I get 0.02 meters squared. And then I just pop that puppy into my calculator, and I got my shear stress at A is 34 megapascals. So this is a case where we saw both single shear and double shear, and so we just have to pay attention to what is going on, what is the physical reality of the situation when we're looking at these things. Let's take a look at one more example. In this example, we're again asked to calculate the average shear stress developed in each 3/4 inch bolt. So we have these 3 boards stacked on top of each other, but we also have 2 bolts. So we kind of have a lot of things going on at once. Let's kind of break out the bolt, each bolt, and look at what's going on with them. All right, so if I break out my first bolt here, this guy comes down through these 3 boards. If I look at what's happening on this pin here, or this bolt that's coming through all of them, I see that from the center board, I'm experiencing this 10 kip force. Right, I get this 10 kip force from this board, and then I'm getting 5 kips each way on top and bottom. I'm getting this shear. I'm getting this shear experienced each way, top and bottom. But because I have 2 bolts, each of these bolts are taking on part of that load. So because I have 2 bolts, instead of the 10 kips it taking on, it's actually only taking on 5 kips because 2 bolts are taking on 10 kips. So what I have when they're working in a pair like this, right, I have these 2 bolts here. Assuming each of them takes on half of the overall load, half of that 10 kip load means that this guy takes 5 kips and this guy takes 5 kips, right? So what we end up with is we have 4 shear areas, right? Because it shears on both the top and bottom from this double shear. We have 4 shear areas sharing this 10 kip load. So we can think of it as like 4 shear areas equals the 10 kips. So our shear is 2.5. Or if we think about each bolt individually, then we can think about it like 2 shear areas per bolt. And each bolt is taking on 5 kips of the 10 kips. Then our shear that we're seeing is 2.5 kips. So that's what's going on in our bolts. Now we should have enough ingredients to go ahead and calculate that shear stress. Shear stress is V over A, and our area, we were given the diameter of the bolt. So our area, again, pi over 4 d squared, so 3/4 of an inch squared. That gives me 2.5 over whatever this number is when I plug that in. Pi over 4 times 3/4 squared. And I plug that into my calculator. And it pops out for me that the shear stress is 5.66 KSI, kips per square inch. So again, the key with this is recognizing how the shear interacts differently when we have different setups, right? Here we had 2 pins, 2 boards, causing this to reduce the force experienced, right? It reduced shear by a factor of 4.